Right, hello everybody, hope you're all keeping well. I've decided to make a little video because I've had quite a few requests to help with the infrared questions that I set you for homework on the email. Now, just to get this clear, infrared spectroscopy, if you're finding it difficult, it suggests that it hasn't twigged with you actually how easy it is. Now, it sounds a bit daft, but I promise you that there's a really, really easy, if you see an infrared question in the exam, you should find it really easy. Okay, so I'll try and demystify it for you. Right, infrared spectroscopy only tells you the functional groups in a molecule. It can only identify functional groups. It doesn't tell you how many functional groups there are. It doesn't tell you anything about their position. It just tells you what functional groups you've got. And it's better for some functional groups than others. So obviously there's a prerequisite here that you've watched the other video that I sent you before. So I'm not going through all of the theory. But remember, the infrared spectroscopy tells you the functional groups. So again, assuming that you've watched the other video, I'm going to now tell you what functional groups it's particularly good for identifying. Now I have printed off somewhere here. Oh yeah, here it is. I've printed off the data booklet that you will get in the exam. Now the data booklet in the exam identifies all of these functional groups with their wave numbers. Now these are the positions where you get the peaks. They're called peaks even though they are actually troughs. So it tells you that you get amines have a peak at 3,300, 3,500 and so on. I'm just going to highlight the ones that are actually particularly useful. OH alcohols is a really, really useful peak. It's really, really obvious. The amines peak is not a very obvious peak. The OH alcohols peak is an obvious peak. The OH acid peak is a very obvious peak. The C double bond O is the most useful peak, I think, in my personal opinion. And the C double bond C is also a very useful peak. The reason these ones are not useful, honestly, I don't want you to ever use them. Do you know the answer? Obviously, I can't check if you're saying anything now, but do you know why we don't use these ones? Or I would encourage you never to use these ones in an exam. Any ideas? Well, it's because these peaks occur in the fingerprint region. Now, I don't want you to go anywhere near these two peaks, all right? Because they're in the fingerprint region. So really, in an exam, all I would expect to see are OH alcohols, OH acids, C double bond O and C double bond C. It doesn't mean to say that the others can't come up. The reason I haven't said that CH is useful is because every organic molecule has got CH bonds. So it's very rarely that can tell us something actually useful. All right. So now, bearing this in mind, then I'm going to show you what my simplified version of infrared spectroscopy means. Looks like, in my head. So I've actually just learned what these peaks look like. So if I draw four axes that represent four different infrared spectra, wave number along the bottom, centimeters to the -1. I'm just going to write centimeters to the -1 and all of this. For those physicists out there, in fact all of you out there, it's a measure of frequency, that frequency of radiation. It's known as the wave number. I'm going to talk to you about the most basic peaks. On each of these, I'm going to write the number 1500 because that is the wave number at which the fingerprint region starts. It's terrible there. All right, 1500, just like being in a lesson, isn't it? Loads of mistakes. But see how we get on. Right, so typically, here we go. This is what an OH alcohol peak looks like. So an OH alcohol peak is incredibly distinctive, and it looks like this. It's broad, it's not sharp or spiky, it's a broad peak. And it occurs, if I look at the data sheet here, between 3,230 and 3,550. If you've got a broad peak that looks like this, it's not jagged in the slightest, that is definitely an OH alcohol peak. That's just what they look like. You often find it right next to some spiky peaks, which are the CH peaks. Okay, but it's this broad peak, this broad sort of finger pointing down, comes really far down. That is an OH alcohol peak. That's what they look like. You'll get some other bits and noise here, and you'll get all of these spiky things here in the fingerprint region, which, guess what? We are not interested in. All right? So in fact, something that I'll be showing you later is one of the most useful tools you've got when looking at infrared spectroscopy is a piece of paper that covers up the fingerprint region, because it does an half make a spectrum look a lot more simple. Alright, so the next one I'm going to show you is a C double bond O peak. Now a C double bond O, or a carbonyl peak, looks like this. There'll be other little noise here and things like that, and then it's a very, very big, sharp peak, not rounded, a sharp peak at around 1700. In fact, the data booklet says it's 1680 and 1750. It goes almost all the way down to the line typically, and it's a sharp peak, like a needle coming down. And then you'll have all this noise and peaks here, which, you know what, we don't look at. Look how simple this spectrum looks if you cover up the fingerprint region. I would look at that and go, oh, there's a carbonyl, there's a C double bond O. Okay, so we're talking here carbonyls, we're looking at, what we're looking at, aldehydes, ketones, well, aldehydes, ketones, for now. The next most common peak, it's a very smudgy pen, sorry about this. The next most common peak that I want to discuss is an OH acid, and the acid it refers to is a carboxylic acid. So we're dealing with an OH that's found in a carboxylic acid. So by their very nature, if you've got an OH acid, you will also have a C double bond O. So what I'm going to draw here is just what carboxylic acid spectra look like. So they have, it says here, the OH acid peak is 2500 to 3000. So it is further to the right than an OH alcohol peak. So I'll try and represent that here. And they are typically broad and slightly jagged. The CH peaks sort of absorb into them a little bit, and they look like that. They are broad and jagged, and then you get this 1700 peak as well. I'm going to move that 1500 along, sorry, just so I've got a bit of room. So you get this combination of a C double bond O peak and this very typical broad peak at around about 2500 to 3000. It's this large peak with an accompanying carbonyl C double bond O spike at 1700-ish. That tells me straight away I'm dealing with a carboxylic acid. Alright, and the fingerprint region, which we cover up. So far, let me recap. We've got alcohols that look like that, a broad finger pointing down, not spiky. Then we've got the spike of a carbonyl at 1700. So the alcohol was around 3000-ish, just above 3000. A carbonyl peak, aldehydes and ketones, are around 1700. And a carboxylic acid has got a combination of a carbonyl peak and this broad lump. Can't really call it a broad lump. Broad peak for an acid OH. The final useful one that I would show you is a C double bond C, which I remember being taught at university is a needle at around 1600. Wave numbers, centimetres to the -1, or wave numbers. So there's 1500. So we'll do that, and it's a needle, a sharp needle. Okay. It's often very small, It can be mistaken for a carbonyl peak, but it is typically shorter. It doesn't extend as far down as a carbonyl peak, and it is more needle-like, which is why my lecturer in university told us about the C1C needle at 1600. It's not always very small. Sometimes it comes down about halfway. Sometimes it's shorter than the one that I've drawn, but you're watching out for that needle at 1600. All right, so for me, these are the four main peaks. We've got the broad finger alcohol. We've got this, which is a carboxylic acid. We've got a carbonyl peak, and we've got a needle at 1600. So I'm tempted here to pause the video, but I'm not going to. I'm going to go straight on then to the infrared problems that I set you. We're going to have a quick look over them first to see if we can spot any of these typical peaks. Now that we know that these are the shapes, we're going to see if we can spot any of them. All right. So here are some spectra, and they just happen to be the problems, the ones that I set you for homework. It's infrared problems too. So I'm not going to look at the whole question yet. I'm just going to see, can I spot any obvious functional groups? Well, if you look here in F, I'm looking at that straight away. Let me just get my very special tool out, which is a piece of paper. It's like being in school, isn't it? Isn't it fun? Isn't this fun? Firstly, I'm going to cover up the fingerprint region. So what are you left with when you cover up the fingerprint region? You're dealing with an alcohol. All right? Straight away, you're dealing with an alcohol. There is your OH peak. It's not that shape. It doesn't even. I don't even need to really look at the number, but it's that broad shape, broad peak at around just over 3,000. It's an OH alcohol, no doubt at all. This peak here is a CH peak. This one, sharp peak at around 3,000, is a CH peak. It is important. It's just that it doesn't really often help us with the questions because, like I say, every organic chemical's got a CH peak. All right. Have a look at this one over here, G, cover up the fingerprint region. Okay. Was that any of the shapes that I showed you on the previous diagram, my simplification of shapes? I hope you're looking at that and you're going, well, that's the carboxylic acid. And you're right, that's the carboxylic acid. It is literally as simple as that. F is an alcohol. G is a carboxylic acid. All right? Because of the shape. You've got this, which is the OH alcohol peak. No, it isn't. It's the OH acid peak, sorry. And this is the C double bond O of a carboxylic acid. So here we've got an OH alcohol. All right. I'll just talk about the limitations of infrared again. Even though this tells us this is an alcohol in F, it doesn't tell us if it's a primary, a secondary, or a tertiary alcohol. It doesn't tell us the position of the alcohol at all. It just tells us we've got an alcohol. So I hope that's clear. Having a look down at these other questions here. Tell me now, obviously you can't tell me now, but say to yourself, what are you looking at there then? What functional groups have you got there? Cover up the fingerprint region, don't even look there. All right, I hope you're screaming at your screen now that it's an alcohol. Yay, because there's that typical alcohol peak. Just between 3,000 and 3,500, it's the broad finger that you only see with alcohols. The broadness and the lack of jagged edges is due to the fact that alcohols typically hydrogen bond, and that causes this broadness. I'm not going to go into too much detail because I'll be out of my depth. This is the CH peak, which you're not going to worry about. Don't get drawn into trying to talk about that peak as anything special. It's the CH peak. Okay. We have a look at this one, and spectrum 10 looks like it's got a lot of peaks going on, but then you cover up the fingerprint region and you realise, well, actually, there's not much to talk about. Okay, apart from this whopper here, which is a C double bond O, because it's at 1700. All right. If you didn't know about covering up the fingerprint region, you'd spend ages trying to work out what all those were, cover them up. You've got a peak at 1700, which is very, very obviously, to me anyway, and hopefully to you soon enough, is a carbonyl peak. These are just CHs. All right, just get used to them. There's always some spikes there. They're just CHs. And this, I'm not really interested in. It's not an alcohol. It's not an OH. It's definitely not the carboxylic acid shape. It's just some other stuff going on. All right. When I look at this spectrum 11, again, it looks very complicated until I cover up the fingerprint region, and suddenly you realise that you've only got these jagged peaks at around 3000, which is CH. Do you notice that? I know it sounds daft, but do you notice how important covering up the fingerprint region is for clarity? Alright, so I've got here, spectrum 9 is an alcohol, spectrum 10 is some sort of carbonyl, aldehyde or ketone, and spectrum 11 hasn't got much going on in terms of alcohols, hasn't got anything going on in terms of alcohols, carboxylic acids, or ketones, aldehydes. Alright, so let's keep looking. Let's go back to... I haven't scripted this or anything, so you are just getting it straight off the cuff, so we'll see how we get on. There's a whole load of other spectra on there, on the second page of these, which if you now, with this knowledge, you might just be able to spot some of those typical shapes. So if I just show you, if you just look at spectrum 3 and 7, do you notice anything about them? Can you say straight away? Do you recognise any typical shapes? Alright, if I cover up the fingerprint region. Yeah, hopefully it's like blindingly obvious. That's an alcohol, it's got that shape, the finger pointing down. They're just the CHs. That's the OH alcohol peak. And we do have to write OH alcohol in the exam. Alright, you can't just put OH, you won't get any credit. And 7, do you recognise that? Well, you cover up the fingerprint region. You've got these two significant peaks. You've got the peak at 1700, which is a C double bond O, coupled with an OH acid. You're looking at a carboxylic acid. But straight away, seriously, I just go carboxylic acid alcohol. I don't give it a second thought. You don't need to. Alright, because that's just the way it is. That's an alcohol, that's a carboxylic acid, end of. 8's an interesting one. You could have a look at that later, but we'll see how we get on. Okay. Right, just looking at the time ticking on here, 17 minutes. I'm hopefully going to do this without having to edit this video. So, because I'm not very good at editing stuff, I haven't really got any editing software. I just want to put it out there as me explaining these questions to you in a one-er. So, let's get on with infrared problems 2, because some people had said they've got infrared problems. Okay, so if the quality isn't very good here, if you can't read the writing, well, print off your own copy, okay? Because I'm not going to risk trying to zoom in here and ruining it. Right then, going to get my book out, going to get my paper out, and I'm going to show you me working these out. Now this is obviously a big risk because I haven't worked them out yet. I'm just going to trust my own intuition here, which could be an absolute disaster. So we'll give it a go. Right, it says here, compound E is a branched chain haloalkane. Right, haloalkane branched chain, okay. So it's got a halogen in it and it's got no double bonds. So already I'm thinking it's an infrared question. There's no double bonds, it's just C's, H's and a halogen. It was found to have the composition by mass of 39.8% carbon, 7.3% hydrogen and 52.9% bromine. Alright, straight away, whoa, it's going to be blurry, sorry. Straight away I'm going empirical formula question. Okay, there were 2 peaks for the molecular ions in the spectrum. Tell you what, straight away I'm going to work out the empirical formula of this. So I'm going to go C, H, O. As soon as I see this, I'm going empirical formula. It's just blindingly obvious to me. So I'm going to go 39.8, 7.3, 52.9. This is what happens when you see this data. You just go straight into empirical formula solving mode. You could divide by the ARs, divide by 1. You can put 1.01 or whatever. It doesn't really matter. That is not an O though, is it? That is a BR. So you can divide by 79.9. Calculator. Calculator is on phone. Phone is being used to record. This could be a hurdle. I've also got a laptop in front of me, so we'll give it a go. That's what you're hearing the tapping now. Password incorrect. Nope. This could be where I have to end the video. No, I'm in. Right. So what I'm going to do now is this sum, 39.8 divided by 12, 39.8 12.8 divided by 12. 3.31, 3.3166, 7.3 divided by 1, I can do that in my head. 52.9 divided by 79.9. 52.9 divided by 79.9. 0.662. 0.6621. Alright, then what I do with these numbers, which don't look particularly useful, I simplify by dividing by the smallest number. So I'm going to divide them all by 0.6621, 0.6621, 0.6621. And that gives me a ratio of one of these. Oh, let's see if I can guess that in my head. That looks about 11, and that looks about... No, that looks about 11, doesn't it? You know what? That's 5:11 to 1. Let's just see that. You know what? I've got the answer sheet here, but that looks like 5:11 to 1 to me. Nice. Yeah, it is. 5:11 to 1. So this gives me an empirical formula of C5H11Br, a haloalkane. There were 2 peaks for the molecular ions in the spectrum at 150 and 152. Yeah, that makes sense. Right, 12 times 5, 50, 60, 78 plus. All right, so the empirical formula, this weighs as it is with the number 79.9 in there or 80 in there. God, that's going to weigh 151. But the thing is, bromine comes in 2 isotopic forms. So you could have C5H11 with a bromine that weighs 79, or you could have C5H11 with a bromine that weighs 81. All right? That's all that sentence means. There were 2 peaks for the molecular ions. All right? Of approximately equal intensity, which tells you that the bromines are in a 1-to-1 ratio. But that's all that is telling you. That is classic sort of distraction from the examiner there to try and catch you out. All right, so I'm pretty confident now that I'm dealing with compound E is a branch chain haloalkane. It's got this formula, C5H11Br. Okay, so before I go on, you could have 1, 2, 3, 4, 5 with the BR there, but that wouldn't be allowed because it tells me in the first sentence that E is a branched chain haloalkane, so it's not that. So we're dealing with something that might be this, with a BR there. We could have the BR on this one, we could have the BR here, we could have branches in different ways. Oh, we need more information, don't we? So we've got to try and work out what this branch chain alkane is from the rest of the information that we're given. Looks like it's going to be a tricky question. I'm getting a bit worried that I'm not going to get it right. So I'm just going to press on regardless. Okay. So we're told then the next bit, E, this branch chain haloalkane, reacts with sodium hydroxide to form F. Alright, so this branch chain haloalkane, let me just write down my thinking here. This branch chain haloalkane, C5H11Br, reacts with, what's it react with? Sodium hydroxide, so OH minus. Well, we know that haloalkanes react with OH minus. They can react to form alcohols, or they can react under different conditions, hot ethanolic conditions, to form alkenes. Alright, I'm looking here. I know that I'm going to make an alcohol, so I'm going to make an alcohol. E reacts with sodium hydroxide to form F, whose infrared spectrum is shown. Alright, well, F is an alcohol. So we're going to make C5H11OH, the alcohol, and that's Fe. I don't know the structure yet, I just know that this is going to happen. What sort of mechanism is this, you lot? If the Br, OH comes in, Br goes out. What sort of mechanism are we dealing with there? Alright, I'll come back to you in a minute if I remember. Probably won't. F does not undergo dehydration with concentrated sulfuric acid. Ah, right. So dehydration of an alcohol is that funny little mechanism whereby an alcohol, any alcohol, will, what's it do? It gains an H+. Hang on a minute, watch this, got a rubber on the end of this pen. Gains an H+, not a very good one, to become OH plus. That goes onto there to become this, and then a hydrogen kicks off to make a double bond. Right. So this statement here, it's hard this statement here that says F does not undergo dehydration tells us a very important fact. It tells us that the carbon that the OH is bonded to, the next carbon along does not have a hydrogen on it. Gosh, okay. Sorry, I was off the screen there here. It tells us that the carbon that the OH is bonded to, the next carbon along does not have a hydrogen on it. So in other words, it's telling us that that's the case. 1, 2, 3, 4, 5. Aha, that was the key bit of information. That F is an alcohol that does not undergo dehydration. Right. Wow, good effort if you've done that at home. That's brilliant, that. Okay. Anyway, the next bit it says, so that tells us an important bit of structure. F reacts further with acidified potassium dichromate. Well, all alcohols apart from tertiary alcohols react with acidified potassium dichromate to form G. Now I look at G and I know that it forms a carboxylic acid. So, what type of alcohols oxidize to form carboxylic acids? Well, the answer is primary, secondary or tertiary, and it's not tertiary. Okay? So, if it's going to form G, which is a carboxylic acid, so C for H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 COOH. If it's forming a carboxylic acid, that means that F must be a primary alcohol. Okay. G is a carboxylic acid. I can see that from the spectrum. So F must be a primary alcohol. F reacts further with acidified potassium dichromate to form G, whose infrared spectrum is shown. And its infrared spectrum shows me that we're dealing with a carboxylic acid by its shape. Draw the structures and name E, F and G. Right, so what you're dealing with here, even though this is called an infrared problem, this is really testing your organic chemistry knowledge. The infrared bit is simple. That's an alcohol, that's a carboxylic acid. Do you understand that? The difficulty of this question is not in the infrared spectrum. That bit's fine. The difficulty in this is knowing what all this other information means. This does not undergo dehydration bit. Alright, so okay, draw the structures and name E, F and G. Identify the species responsible. Right then, so I got most of my information from the question that said, from the bit that said it does not undergo dehydration. So I know it was an alcohol, and straight away I got this structure. So actually this is the only alcohol with that formula, C5H11OH, that does not undergo dehydration that I can think of. I'm going to have to check the answers in a minute and re-record the video if I get it wrong. I'm not putting any double bonds in because it said it's a haloalkane originally. Right, let me just count this up. 1, 2, 3, 4, 5 carbons. It's branched. 1, 2, 3, 4, 5. OH, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 H's and an OH. That is C5H11OH. So far, tentatively, I'm happy with that as being F. That must have come from. Hey, I think I'm onto something here. That must have come from this haloalkane. Yep. And then that must have formed CH3, CH3, CH3. Sorry about that, that's awful, isn't it? Shouldn't do that. CH3. COOH. Just Just going to neaten this up a bit with my magic pen rubber thing. Right, I think that's it. Okay, so what happened then? I'm going to go through the old question. This is E. I worked out the empirical formula using the way that you work out empirical formulas. Empirical formula, you just should be able to do it. If you don't know how to do it, use the lockdown to teach yourself. Alright, it said it reacted with sodium hydroxide. That's because this happened. There's your nucleophilic substitution reaction. See, I did remember that question. Nucleophilic substitution. That makes this alcohol, and this alcohol is a primary alcohol. Notice it's a primary alcohol because the carbon it's attached to is only attached to one of the carbon. Alright, this primary alcohol is oxidized by acidified potassium dichromate, K2Cr2O7, to make the carboxylic acid. I asked you to research how that works, and I hope you'd know that that would be under reflux. Alright, you oxidize it and oxidize it. Primary alcohols oxidize to aldehydes and then eventually to carboxylic acids. And the little bit of information that was crucial to this was finding out that F does not undergo dehydration because there is not a hydrogen attached to this carbon. That was the hard bit of the question. Okay. Right, before I go on to the next bit then, you'll find in exams that they really like linking infrared spectroscopy to alcohols and alcohol oxidation. Just going to remind you of this little diagram. This was just before the lockdown. I showed it to you, but not in enough detail. There are three types of alcohol: primary, secondary and tertiary. This is what I like to call my oxidation triangle. Primary alcohols can be oxidized to aldehydes, which can then further be oxidized to carboxylic acids. Secondary alcohols can be oxidized to ketones. Notice there's no hydrogen here, and they cannot be oxidized any further. And tertiary alcohols just cannot be oxidized. So I always have this in mind when they're talking about oxidation of alcohols. That square bracket with an O in it just means oxidizing agent. So it means things like if you leave ethanol, for example, in wine, out in contact with oxygen in the air, the ethanol will turn into an aldehyde, and then it'll turn into ethanoic acid, ethanol, and then ethanoic acid. Long story short, your wine will go off and the alcohol will taste like vinegar. So primary alcohols oxidize to carboxylic acids. Secondary alcohols oxidize to ketones. Right, so in terms of infrared spectroscopy, what you would see with this is if you were following this oxidation in infrared spectroscopy, you would see sort of looking like that, but I can't bother drawing the fingerprint region. The aldehyde, the alcohol peak would disappear and you'd see a sharp peak at 1700. And then if you left it under reflux for ages, you would see this broad peak with the sharp peak. And it would do that. And I would go alcohol, obviously an alcohol, they're just the CHs there. C double bond O at 1700. And then this is the distinctive carboxylic acid peak. Alright. Secondary alcohol, very similar. You'd see the alcohol peak, and then you'd see it turn into a carbonyl peak at 1700. You'd see that. Okay. So, next question. I'm tempted, right? Well, one, because this video is already 34 minutes long. I think I'm going to leave question 3 for you to work out yourselves. See how you get on with this little video. But I'll go through question 3 in a separate video. See how this one goes down. See if it's useful to you. So I'm thinking I'm going to go through question 2 now, which is this. And I'm going to leave question 3 for you to have a go at now that you've got this hopefully simpler idea of what infrared spectrum is. Spectra are, sorry. Alright, so let's just try this one. Question 2. So hopefully you've given it a go already. So you're looking at this video because you've failed on it, or you've struggled on it, sorry. So I'll see if I can work it out on the sheet with you. Again, I've not looked at this one yet, so I'm going to try zooming in without ruining all of this. Ooh, okay. I'll have to show you the setup that I've got here. I've actually made a camera stand out of Duplo. That's how resourceful I am in it. COVID. Resourcefulness. Check that out. Clever that, innit? You don't have to answer that. Okay, propene reacts with HBr. Right, propene. So just start off, they're not going to... You don't want to be straight away going, oh, it's all like foreign language. You start drawing it straight away. Propene reacts with HBr. And you go, yeah, I know it does. HBr is going to add over that propene to form H. Okay, so down the side here, I'm going to go propene. There's propene reacting with HBr. Right. So, you're either going to get a Br here and an H here. Love this rubber. Check that out again. I think I've said check that out every time I've used this rubber. It's not that exciting, is it? Right, you're either going to get that, or... Oh, it didn't rub out that well that time. I'm not that impressed, actually. That's better. Seems to be coming back. Anyway. Or you could get H and a BR there. Alright? Yeah, I'm not that impressed with this rubber. There you go, I'll rub them both out and put a big bond in there. Okay, so that's the first sentence. Propene reacts with HBr to form H. And I would expect you lot to just go, yeah, I know it does. Yeah. And you're either going to get 2 bromopropane or 1 bromopropane. So one of these is H. H reacts with sodium hydroxide to form I. And okay, so H reacts with sodium hydroxide. Well, these are going to react with sodium hydroxide to form I. Okay, so that's either going to be nucleophilic substitution or it's going to be elimination. Okay, I'm already looking here. I've got an alcohol peak, so I'm thinking what's going to happen here is reacts with sodium hydroxide is OH minus acting as a nucleophile. So, going to show my thoughts here. Either that's going to happen. Yeah, I remember when we did this in class. Remember school? Oh, that's weird, isn't it? Out of focus there. Okay, that goes to there, and that goes to there. Oh, it doesn't half go out of focus when I write on it. Sorry if that's been happening all the way through. I haven't noticed that before. Okay, so nucleophilic substitution, minus charge on there. So I is going to be either C with an OH there, or C with an OH there. Okay, and these are going to be I. So basically what this question is, we're going to try and work out whether we're going to go with the interesting functional group in position number 2 or the interesting functional group in position number 1. Okay, so H reacts with sodium hydroxide to form I. So one of these two is I, one of these two is H. I reacts with warm acidified potassium dichromate, or an oxidizing agent, to form J. The infrared spectrum of H, I and J are given below. But it does indicate the infrared. But it does indicate which is which. What? But it does indicate. Well, I think that's a typo. But it doesn't tell you. It doesn't. I think I was meant to say it doesn't indicate which is which. Identify the 3 compounds H, I, and J using the infrared spectra below. All right, let's have a quick look then. So what we've got then is we've got an alcohol here. So this must be I. Because I are the alcohol. So this is I, because it's an alcohol. And I would say in the exam, because it's got an OH alcohol peak between, and I've got my little sheet here, I'll just copy off the sheet, between 3230, and 3550. That's why that's I, because I is an alcohol. 10, right, I'm going to see if there's a, going to go across there. 10 has got a carbonyl peak. So 10 has got a C double bond O. That is telling me, right, that's to do with, it says here, I reacts with acidified potassium dichromate to form J. Alright, when you react an alcohol with acidified potassium dichromate you're going to get either that ketone, propanone. You don't need to say propan-2-one, because if it was on the ends it would be propanal, or you get propanal. Excuse the laziness missing off the hydrogens. You're not allowed to do that. I am, because I'm a grown-up. Okay. So let's have a little look at what we've got then. We've got, this has got a carbonyl peak, so this must be J. J carbonyls are there. I'm interested by this because this is clearly not a carboxylic acid. Therefore, I'm going down the route that this is J, because it says if this one, probably, if it was a primary alcohol, we probably would have made the carboxylic acid there. And I don't think, this isn't a carboxylic acid. Alright, so this is J. I'm going to put a big J over that. I hope I don't have to re-record this because I'm scrolling all over this. That's J because it's got a carbonyl peak. It's an oxidation product because it's got a carbonyl peak. This is I because it's got the alcohol in. And this one, therefore, by elimination, must be H. Well, if we look at H, H was, we think, is this. In terms of infrared, that is a very, very boring molecule. It's got C's and H's, and it's got C's and BR's. Well, you'll notice on your data sheet that C and BR doesn't make any appearance. Look, no CBRs. So you cover up the fingerprint region, and all you've got on H is the peak for the CHs. In other words, there aren't any functional groups of interest in H. Therefore, it must be, well, it's that. Okay. There's no C. There's why you'd say, why is this H? Because there's no OH peaks, no OH alcohol peaks, blah blah blah. There's no C double bond O peaks. Why is this J? Because J was an oxidation product, and you've got a C double bond O peak there, and I is an alcohol peak because it's got that peak there. All right. God, what a mess! When I'm looking through the screen at that, that is a scrawly mess. Okay, so identify the three compounds H, I, and J using the infrared spectrum below and decide which spectrum belongs to which compound. Right, let me reiterate this fact and re-emphasize this fact. Infrared is not hard, but organic chemistry is tricky. That's the bit that's hard here. Identifying the infrared spectra is not the hard bit. Knowing your organic chemistry inside out, knowing your mechanisms, knowing what phrases like it was oxidized or it was reacted with acidified potassium dichromate, knowing that that means you're going to be dealing with this triangle and aldehydes and carboxylic acids. Knowing what the clues are, that's the hard bit. All right, so I'm not going to go through this last question. I'm just going to prep you for it. All right, your first job then on this last question is to draw these compounds. Hex-2-ene, so pentane, methylpropan-1-ol, one, methylpentanone, butanal, butanoic acid. All right, and straight away I'm going to go to you, right? I know what these spectra are going to look like anyway. As soon as you cover up the fingerprint region, you can do it here, look, you can go all the way along there, cover up all the fingerprint regions, and straight away, I'm just going to zoom out of it again, try not to break my Duplo. Straight away, I'm looking down there and I can see which ones are interesting. This one, alcohol. This peak here, C double bond O. This peak, C double bond O. Alright? That's just CH, that. That's just CH. Don't be drawn in by the CH peaks because they're always there. Look, not interesting, not important. They like to make you think they're important, but they don't help you at all. All right, I'm looking down these ones here. Cover up the fingerprint region. What have I got here? I've got, that's at 1500. CH peak. Nothing going on there. Okay, you get what I'm saying? And then you look at your compounds and you go, right, what would you expect to see? Hex-2-ene. Well, hex-2-ene is a load of CHs and a C double bond C. So you go to yourself, well, what are you expecting to see? Well, I'm expecting to see, well, some peaks are the normal CH peaks, but I'm expecting to see a needle at 1600. Pentane, you're only going to see that boring CH peak. Methyl propan 1-ol. Methyl propan, CHs, ol. You're looking for that peak at 3000, etc., etc. Do you get what I'm saying? I don't know what, it's a rhetorical question. I hope you're all at home going, yeah, I think I do. You can guess what these are going to show before you even look at the spectra. There are only 4 simple shapes to learn, and they are, just to remind you, alcohol, carbonyl, alcohol, carbonyl, alkene, maybe should have made that a bit smaller, and the final one, very distinctive, carboxylic acid. Alright, I hope you found that useful. I'm probably going to watch this back now and realise it was awful. I don't half go on, don't I? That's like one of my lessons, that 46 minutes I've been talking, and that was meant to be just going through one question. I hope you found it useful. That's how I would teach it in a lesson. I would try and convince you that, you know, infrared spectroscopy is not particularly difficult. Cover up the fingerprint region always. Don't delve into the fingerprint region at all, so don't use these. Anything else to add before I go and have a cup of tea? No? Hope you're all well, and hopefully see you sooner rather than later. There will be no comments on this video, obviously, they'll be closed, but please feel free to email me with any questions. Alright, bye.